Let's finish off chapter 7 by talking about the law of cosines. We've talked about the law of sines extensively and used it. We haven't yet introduced the law of cosines. Now, just one thing to note, we are going to talk about Heron's formula and how to derive it, but we're going to move it to the end. So I've just rearranged the order of my pages. I think that started out as the third page of notes, and I have shifted it to be the last page of notes. Okay. With Heron's formula, that's how to find the area. And with Heron's formula, we have to know semi-perimeter. Hopefully that's easy for you to figure out that semi-perimeter is just half the perimeter, and perimeter is distance around any shape. So that's semi-perimeter, but that's our vocabulary word that's going to go with Heron's formula. Triangle side length restriction. In any triangle, the sum of the lengths of any two sides must be greater than the remaining side. Now, why? If you think about this in terms of maybe ladders, this might make sense. If I give you a triangle and I say that it's got sides of 15, 7, and 7. Well, is that possible? Okay, think about it this way. What if I've got two people standing across from each other here, and each of them is holding a 7-foot ladder. And they're wanting to make this peak in the middle, lean the ladders up together for some reason. Maybe they're going to dangle something from it. I don't know. But they start 15 feet apart. If they are standing 15 feet apart and they start to lean their ladders toward each other, and their ladders are 7-foot long ladders, is this possible? Is this possible? Well, no, this is not possible, because if this ladder is 7 foot and this ladder is 7 foot, even if I just laid them down on the floor, that 7 and that 7 are not going to meet, because 7 plus 7 is 14. I have a gap. Even if I just lay them flat, I have a gap. That is not possible. Those measurements for a triangle will not work. So the sum of two lengths has to be greater than that third side, or the ends won't meet and I won't have a triangle. Would this triangle work? Let's do this one. Let's do 5, 6, and 12.7. Well, that's not going to work either, is it? That's not possible. Because 5 and 6 is 11, they are not going to meet. They're certainly not going to meet and form a peak. I couldn't even lay them flat and have them meet, because the sum of these two is just 11. So these are not possible configurations for sides of a triangle. Moving on into law of cosines. Now let's look at the law of cosines. So for the triangles we have been working with have allowed us to pair up an angle and an opposite side so that we can use our law of sines. But if we don't have that pair, if we don't know an angle and the opposite side, then we can't use the law of sines. We can, in that case, use the law of cosines. Now, I have 3 different versions of the law of cosines. You don't need to stress about remembering each of the versions. Of course, you're going to have your identity page. What you need to do is notice the pattern. If I know angle A and I need to find side A, then I have A squared equals the other two sides, sum of those squares, minus 2BC. So the product of those two sides and 2 cosine of angle A. So if I know angle A, it's set to equal to side A. If I know angle B, it's set to equal and solve for side B. If I know angle C, we're set equal to solve for side C. Now notice that each of these is squares, so to solve for that side, I would take the square root of the right side of my equation. Whatever I'm solving for, I use the other two sides here and there for the sum of the squares and for that product. If I'm solving for B, I have the sum of the squares of A and C and the product of 2AC. Etc. Now, something that's really interesting, if angle C is 90 degrees, then what's the cosine? Well, the cosine of 90 degrees, or the cosine of C, is 0. Cosine at 90 degrees is 0. Therefore, so if I look at this third case, I would have c squared equals a squared plus b squared minus 2ab cosine C, and we just said at 90 degrees, where my angle is 90 degrees, cosine of C is 0. So I've got C squared equals A squared plus B squared, and hopefully you identify that as the Pythagorean theorem. The Pythagorean theorem is really just a special case of our law of cosines. So you've been doing the law of cosines and you didn't know it. Every time you did the Pythagorean theorem, it's just for that right angle. If we fill in our text below, according to the law of cosines, the square of a side of a triangle is equal to the sum of the squares of the other two sides minus twice the product of those two sides and the cosine of the angle included. So when we are using law of cosines, we're starting with that side angle side information. When we're using the law of cosines, we need to remember about our restrictions for our inverse functions, because that's going to make a difference to us. So I want you to remember when I have sine inverse and when I have cosine inverse, and we're only going to talk about specifically sine and cosine this time right now because these are the two that we are dealing with. Sine inverse is restricted to quadrants 4 and 1. Sine is negative in quadrant 4, it's positive in quadrant 1. If I use sine inverse on my calculator, it's going to return an angle in one of these two quadrants. If my sine function value is negative, I get an angle down here. If my sine function value is positive, I get an angle up here. This angle that it returns is going to be a negative acute angle between 0 and 90 degrees. This angle, if I start with a positive sine function value that it returns, is going to be a positive acute angle between 0 and 90 degrees. So if I'm using sine inverse, it will never return an obtuse angle. If I'm using sine inverse, I'm going to get an acute angle measure. What about cosine inverse, however? Cosine inverse is restricted to quadrants 1 and 2 because cosine is positive in quadrant 1 and negative in quadrant 2. So if my cosine function value that I start with is positive, it gives me an angle between 0 and 90. If it's negative, it gives me an angle between 90 and 180. Acute angles in quadrant 1, obtuse angles in quadrant 2. Therefore, if the cosine value that I'm starting with is negative, if the value is negative, the angle that returns when I use it in my calculator is obtuse. So sine inverse will never give me an obtuse angle, whether it's supposed to be or not. Cosine inverse, if I have an obtuse angle, it will show up. Now, this is why this is important, guys. We're going to go through and we're gonna lay out the order and why things work, but let's look at something first. Let's say that, and I'm kind of jumping the gun on this a little bit, but I just want to show this to you. So kind of put your pencils down and just walk through this with me. I've got a triangle, and this is what I'm given. I'm given the lengths of sides B and C, and I'm given the measure of angle A. This is my side angle side. I can't start with law of sines. I have to start with law of cosines because I don't have information I need to use law of sines. So I'm going to have to solve for side A using angle A in my law of cosines. Now you can look back to see what that looks like, but basically side A is the square root of the sum of the squares of the other two sides minus 2 times the product of those two sides times the cosine of my angle. When I simplify all of this, I get that side A is 9.4 inches. Now I know side A, which means I have a pair. And I can use law of sines now to help me find either angle B or C. Now I only have to find one, and then I know that the sum of the three angles is 180, and I can just subtract to get the third. But I have to use law of sines to find either angle B or angle C. If I start with angle B, this is what my law of sines looks like. and I get that B would be 67.9 degrees. And if B is 67.9, A was given as 38.8, that means angle C has to be 73.3 degrees. However, if I start with law of sines to find angle C, I get angle C as 29.1 degrees, not 73 degrees, and that would make angle B 112 degrees obtuse. But side angle side is not our ambiguous case. That's not our ambiguous case. However, because of the way it's set up, I can make it turn into what looks like an ambiguous case by choosing the wrong way to go. Which one of these two is correct? Well, this one is correct. I should always start with the smaller angle, because if I'm using law of sines, remember what we just said. If I use sine inverse law of sines, I'm never going to get an obtuse angle. I'm not. So if the angle I'm looking for should have been obtuse, it's going to be returned to me as acute, even if it should be obtuse. I can fix that. I can avoid that issue by when I start with law of cosines and I move to law of sines by always choosing the smaller of the two angle choices. Remember when we were up here, we know angle A, we need to find angle B or C, and I need to know which one to try first. Well, if I try the smaller one first, I know it's going to be acute. I can only have one obtuse angle, and the smaller angle couldn't be that obtuse angle. It would have to be the biggest angle. In this triangle, which angle is going to be the biggest angle? Well, the biggest angle is opposite the largest side, or the longest side. So angle B for this triangle would be the biggest angle. If I'm going to have an obtuse angle, it will be this one. It can't be angle C. Angle C is opposite the shortest side, so it has to be the smallest angle. That's the angle I'm going to find using law of sines. Because I know angle C is acute, and I know that using sine inverse with the law of sines will give it to me as acute. Whereas B is the largest angle in my triangle, it could be obtuse. But if I try to find it using sine inverse, it won't come back obtuse because of where sine inverse is restricted. Okay, let's fill in that next page of notes. This gives us kind of a good go-to when I'm deciding how to work through a problem and where I go to look. Just a quick reminder about what we just talked to. Reminder, sine inverse is restricted over here in quadrants 4 and 1. Cosine inverse is restricted in quadrants 1 and 2. Sine inverse will not give me an obtuse angle. Cosine inverse will give me an obtuse angle. Okay, case 1. We have 4 different cases of oblique triangles. Case 1 is when we know one side and any 2 angles. Every single time, if I'm given one side length and 2 angle lengths, the first thing to do is find that remaining angle. To find that remaining angle, I use my angle sum formula. The angle sum formula is simply that knowledge that if I add the 3 angles together, their sum is 180 degrees. Once I know all 3 angles, I can find my 2 missing sides, and I can just use the law of sines for both of those sides. Because I'm starting with a situation where I know a pair, so I can use law of sines. Case 2. Case 2 is my ambiguous case. Remember, case 2 is my ambiguous case. We know that going in. If I'm given 2 sides and 1 angle where that angle is not included between the 2 sides, I have my ambiguous case. I might have 0, 1, or 2 triangles, and I have to figure that out as I go. The first step is to find one of my other angles. I've got one angle I know, and I know the side opposite it. I will find the angle that's opposite this other side. I only have one choice here. I will find an angle using the law of sines. That's where I start. So that's the first angle is given. The second angle is found. I use the angle sum property to find the third angle. And then I have one side left to figure out. So I use law of sines for it. And then I remember to check to see whether or not two triangles exist. I may have to go through the steps again. All right. Then we move over here to the next one. Case 3, not my ambiguous case, where I have side angle side. That known angle is between the two sides. This is not ambiguous. I know my included angle. That's the important difference between case 2 and case 3. It is not ambiguous. But remember that example I just showed you? But you can end up with that situation. If we're not careful, if we don't choose wisely, in step 2, we could end up with an ambiguous situation. And it's not ambiguous, so we need to make sure we choose wisely. Okay, if I have side angle side, that means I don't know a pair. I know maybe A, B, and angle C. Side angle side. So I don't know this opposite side, which means I can't use law of sines. I have to use law of cosines. Now, when I use law of cosines, that's step 2. This is the important thing. Find the smaller of the two remaining angles using law of sines. That smaller of the two is important because if it is the smaller of the two remaining angles, I know without a shadow of a doubt, I know it's acute. If it's the smaller of the two, I know it is acute. It can't be obtuse if it's the smaller of the two remaining angles. So I know it's in quadrant 1, no matter what. I know it has to be in quadrant 1. I don't have to worry about it being an ambiguous, I don't worry about ending up with something incorrect. Now I've been given an angle, I found an angle, I'm going to use my angle sum to find the third angle. Then my fourth case, the last case, is side, side, side. Side, side, side is not ambiguous. And so I've got to start finding an angle. If I don't know an angle back here, just again, I don't have that pair. So I have to find an angle before I can use law of sines. So I have to use law of cosines. Now with law of cosines, remember cosine inverse will give me that obtuse angle if it exists. So when I'm using law of cosines, I'm looking for that largest angle. How do I know which one's my largest angle? Well, that largest angle is opposite the longest side. So if there is an obtuse angle, if there is an obtuse angle, we found it. And we don't have to worry about it again. If there's an obtuse angle, it's found, it's out of the way, and we don't have to worry about it. So after we've used this law of cosines once, we're going to switch to law of sines. And it says find either of the two remaining angles, which is absolutely true. But if you get in the habit of when you're using law of sines starting with the smaller, then you won't forget to do it when it matters in that case 3. And once you know two angles, you always find the third angle using the angle sum formula. Okay, why are we switching from law of cosines to law of sines in both of these? Well, law of cosines is a lot more work than law of sines. That's just what it is. Arithmetically, it takes a lot more work. It lasts a lot longer trying to solve, and you have more chance of making an error with law of cosines. So when we can use law of sines, we choose to use law of sines. Work smarter, not harder, right? All right, let's do some examples where we need to use law of cosines. For this first 2 examples, we're not solving the triangle, we're finding a specific piece of information. It says 2 boats leave a harbor at the same time, traveling on courses that make an angle of 82 degrees 20 minutes between them. So I have 2 boats leaving the harbor. Got this harbor here. And they leave at an angle from each other of 82 degrees 20 minutes. When the slower boat has traveled 62.5 kilometers, so let's just make this the slower boat, The faster boat has gone further, obviously, 79.4 kilometers. At what time, at that time, right then, what is the distance between the boats? Well, the distance between the boats is, the shortest distance is a straight line, right? So this is what I'm looking for, this distance between the boats. I'm looking for that third side. If we put some labels on things, let's maybe do A and B as our boats and C as our harbor. That means we are looking for side C. Well, let's go apply our law of cosines. We can't use law of sines here because we don't have a pair. We don't know the angle on the side opposite it. We have side, angle, side given to us, so we have to use law of cosines. The law of cosines that applies here, I'm solving for C, so I have C squared equals A squared plus B squared, the other two sides, minus 2AB, again, the other two sides, times cosine of C, which is the angle that we know. To solve for C, I will have to take the square root of all that. And I'm going to plug in everything that I know. Now this turns out just to be really a long calculator math problem. I just have to be cautious about how I plug it into my calculator. Make sure that I'm careful about being in degree measure, first of all, because angle C is given to us as 82 1/3 degrees, 20 over 60, so 82 1/3 degrees. I'm going to, now, when I take the square root to solve, we typically consider plus or minus, but this C value is a measure of distance. It's going to be positive. We don't have to worry about plus or minus here. So I square this term, I add the square of this term, and then I subtract this product where I'm in degree mode. Make sure you're in degree mode. What you should get, and this is rounded off, do not round it off until the very, very end. But when I plug all this into my calculator, I should get 8,886.5 something, which is approximately, and now I'm going to go back to my problem, and I see that I have 3 significant digits, so I want my answer in 3 significant digits since I haven't been told differently. All right, look at the next one. Pause the video, see if you can sketch the next situation and set up your law of cosines. Once again, you should have your sketch. You're solving for C, and it did give you labels this time, A, B, and C. So it tells us what we're setting up and solving for. When I plug that all into my calculator, I should get this huge number. Let's see, 394,510, and I'm going to round it off. Don't round it off. Just do second square root of that answer in your calculator so that it doesn't round it before the end. You don't want to take a chance on rounding it off and altering your answer so that it's not correct if you round too soon. Once more, I wasn't given rounding instructions, so I used significant digits, and my problem has given me 3 significant digits. Don't forget your units. Whenever you're doing an application problem, make sure that when you have units, that you answer with those units in your answer. For example 2, we are going to be solving the entire triangle. So we want to find, we're given 3 pieces of information. We need to figure out what 3 pieces we're missing and find all 3 of those pieces. ABC is my triangle, and it doesn't matter how you sketch it. You just need A, B, and C. Angle B is 73.5 degrees, 73.5 degrees. Side A is 28.2 feet, and side C is 46.7 feet. If it hadn't already told me, I would see that I have side, angle, side. I do not have the pair of an angle with its side length opposite known, so I have to start with law of cosines. That's going to be my first step, is law of cosines to solve for side B. If I'm solving for side B, I have B equals square root of A squared plus C squared minus 2AC, because those are the sides that I know, times the cosine of angle B. Plug in all those values. And I'm going to round it to 3 significant digits again, so that I get side B is about 47.2 feet long. So now I know all 3 sides in my triangle. I know side B is about 47.2 feet. I need to find angle A and angle C. To find angle A and angle C, well, to find one of them, I'm going to use the law of sines. To find the other, I'm going to use my angle sum theory. For law of sines, I need to use the smaller angle first. That's the one I'm going to look for, the smaller of the two. Well, which one of these two, A or C, which one's smaller? The smaller angle is opposite the shorter side, so the smaller angle is angle A. So I have sine of A over 28.2 feet is equal to the sine of that 73.5 degrees, the angle I know, angle B, over that found value. Now we always want to use our givens as much as possible. This is a situation we have to use a found value. If this is wrong, it's going to throw off the remaining two answers. So do your best not to round to the end to be as accurate as possible with that found value that you have to use. Law of sines, I solve using cross products so that I get the value for sine A as 0.57285, and then I have to, that's rounded. I won't round it. I'll just use everything that's in my calculator and do inverse sine of that, making sure I'm in degree mode, so that I get an approximate value of angle A as 34.9 degrees. And then once I know angle A, I was given angle B, I can find angle, whoops, this is the third step. I can find angle C, measure of angle C, by taking 180 degrees and subtracting the two angle values that I know. So that angle C comes out to be 71.6 degrees. All right, let's do another. Start by sketching your givens. This time I'm given angle A, I'm given side B, and I'm given side C. So I need to find side A. That's my first step, is to find side A. Side A ends up being about 10.5 meters. And then once I know the length of that side, I'm going to switch and find the smaller of the two angles. My second step is to find the smaller of those two angles. Which one's smaller, B or C? Well, the smaller angle is opposite the shorter side, so my smaller angle is angle B. Because I chose the smaller angle, I know it is acute. So when I use sine inverse, it's going to give me the right value. So I get an approximate value for angle B as 55.8 degrees, rounded to 3 significant digits. Using that angle sum theory, I figure out that angle C would be 81.9 degrees. Now, here's another example. Angle C here, that's really close to 90 degrees. If I had used law of sines here, if you want to go back and play with it, you can. If I'd started finding angle C using law of sines, well, it is acute. It would come back acute, but if it were just a little bit more off, it would have given me acute whether it was obtuse or not. Okay. Since I'm looking for angle C, I want to make sure that I am using the correct law of cosines because I don't know any of my angles. I'm going to be finding angle C. If you remember, we've already rearranged our law of cosines to represent what happens when we find an angle value. So if I'm finding cosine C, I have C squared minus A squared minus B squared divided by 2AB. Cosine C ends up being negative 76 over negative 132 when I plug in my known values, which is approximately 0.57 repeating. So angle C, when I use cosine inverse for that value, comes out to be about 55 degrees. Then it asks us to go back and find angle B. You're going to use the same process, but this time I'm solving for cosine B. So I start with B square and subtract A square and C square. My denominator is negative 2AC. Those are negatives right there. So for cosine B, given the problem that I'm working on, I get a negative 166 over a negative 198, which is approximately 0.83 repeating. So angle B should be about 33 degrees. Don't forget to use your degree symbol when you are writing a degree measure. Our final page is Heron's formula for the area of a triangle. We have one other formula for the area of a triangle. Depending on what information you're given, you're going to pick and choose which of those two area formulas to use. Use the one that gives you the least amount of work to set up. If I know my three sides, I can find the semiperimeter. Semiperimeter is just half of the perimeter. The perimeter is where I add the three side measurements. The area then is the square root of the product of the semiperimeter multiplied by the difference between that semiperimeter and each of the three sides. And that's what this explains right there. Let's do a couple of examples using Heron's formula to find the area of a triangle. It says the distance as the crow flies, so just straight across from Chicago to St. Louis, and then St. Louis to New Orleans, and then from New Orleans to Chicago. All right, let's draw our triangle. These cities are vaguely triangularly oriented to each other, where we've got St. Louis out here, Chicago up here, and New Orleans down here. The distance from Chicago to St. Louis is 262 miles. From St. Louis to New Orleans is 599 miles. And from New Orleans to Chicago is 834 miles. What's the area? Okay. To find the area, I first need to know the semiperimeter, which is half of the perimeter, A plus B plus C. So I add up the three side lengths and I divide it by 2 or multiply by a half, however you prefer to set that up. And I get a semiperimeter value of 847.5 miles. Then I'm going to use that in my Heron's formula for area. Heron's formula says I take the semiperimeter, and then for my other factors, I'm subtracting each of my side lengths from the semiperimeter. So I have S, 847.5, and then S minus side length A would be 585.5 for the way I set up the problem. S minus side length B is 13.5, and S minus side length C is 248.5. Now let's say that you labeled your sides A, B, and C differently than me. That doesn't matter, because when I'm multiplying terms, order does not matter. 2 times 3 is 6, 3 times 2 is 6. Order does not matter with multiplication. So I find this product of these 4 factors, and then I take the square root of that value. When I do that, I get approximately 40,800 square miles, keeping it to 3 significant digits. Notice that it tells us to ignore the curvature of the Earth because those curved triangles have actually more than a sum of 180 degrees. We're just going to consider it as a flat triangle. All right, the next one, we've got Los Angeles, New York, and Montreal. Los Angeles, New York, and Montreal. If we kind of sketch those, we get LA over here, we've got Montreal up here in Canada, and we've got New York over here. The distance from LA to Montreal is 2,427 miles. The distance from LA to New York is just barely a little farther at 2,451 miles. And then the distance from Montreal to New York is just 331 miles. Remember, I first need to know my semi-perimeter. For this problem, when I add this up and divide by 2, I get a semi-perimeter of 2,604.5 miles. And then I use that in Heron's formula. I take the semi-perimeter times the difference between this value and each of those sides. I'm going to allow you to set that up. That comes out to about 401,664 miles. If I round it to 4 significant digits, I would get 401,700 square miles. That's 4 significant digits, but I just noticed this only gives me 3 significant digits. Just pay attention in my math lab to what the problem is asking you to round to.